To the second analysis junior seminar of this year. Okay. Just to inform you that we record the seminar, and the recording will be found in the YouTube sister channel. So we have Martina Zizza as the speaker of today from Zizza, under the supervision of Professor Bianchini, that we talk about dynamic blocking problems of fire propagation. Thank you, Martina.
Okay. Thanks, Simone and the organizers for the invitation. Today I will speak about the fire problem, and what I want to say is that this research topic was started by Alberto Bressan in 2007. So it's a very recent topic, and there are many open questions and really few mathematical tools to treat the problem. So I think it's interesting to give an overview of the result in literature and to show you what we achieved. Very few things, but so I start. We consider the fire that starts spreading in the unit wall. So as in the picture in the slides, we have the starting region at 0, which is the unit wall centered in the point F, in the plane R2. And we assume that at time t equals 0, the fire starts spreading in all directions with speed equal 1. Okay, so the model of this problem is the following. So one consider the Cauchy problem. X dot is in f of x, and x is 0 is in the starting region at 0, where f is a closed unit wall. Is unit wall, yes. So this is a differential inclusion. And it means that the speed varies. The speed varies in the closed unit wall. So at every point, I can choose to go following the speed in the unit wall. So this is the meaning of differential inclusion. And for this kind of problem, the reachable set, or the region burned by the fire at time t, is the set of x and t, such that x and 0 is in R0, and x dot of tau is in f x. So almost every is 0. So this is the region burned by the fire. So while the fire starts spreading, we have some firefighters that decide to construct some barriers. Okay. What is a barrier? Maybe, yes. Okay. So a barrier is a set value function T gamma T, to the gamma T in R2, which is a one-dimensional rectifiable set. And it satisfies the following properties. Gamma of S is contained in gamma of T whenever S is lower or equal than T. And H1 of gamma of T is lower or equal than sigma T for every T, where sigma is a positive constant. Okay, so just an explanation. We have these barriers that are one-dimensional rectifiable set. This set grows in time. It means that if my firefighters put the barrier in the region of the plane, then this barrier cannot move in time, it's fixed, and it's growing. Then this requirement is that the length of the barrier constructed until the time t has to be lower or equal than sigma t. So sigma is the construction speed, the speed of the firefighters that construct the barrier. So the fire problem is about the confinement of the fire. So we are interested in understanding, depending on the choice of sigma, if at some time t, finite time, the firefighters can block the fire. And to write this fire problem, we consider the burned set, so the reachable set for the differential inclusion, and we call R gamma of T the same set, but with the property that X of tau does not lie in gamma T for every tau in 0 T. So is the reachable set in the presence of barriers. We define at this point R gamma infinity as the union over the time t of R gamma of t, and we say that gamma, which is an admissible strategy, so this is the admissibility conditions. Gamma, people from home can, okay. So gamma is admissible blocking strategy if R gamma infinity is bounded. Okay, so we want just to understand if the total region burned by the fire is bounded. Okay, so the question is, can we confine the fire? There is this theorem of Bressan, so I start erasing the black block. So we have the following theorem. The sun. So if sigma is strictly greater than 2, then there exists always an admissible blocking strategy. Okay. What happens? Okay, there exists always an admissible blocking strategy. How is this strategy constructed? We have the starting region of the fire, and then my firefighters, I have two firefighters, and then they start to construct a branch of a logarithmic spiral here and another branch here. And they, if sigma is greater than 2, these two branches close. And we have a half. Why the logarithmic spiral? So these logarithmic spirals are quite important in this kind of problems. So logarithmic spiral is the following curve. And if this is the center of the spiral, so you have to imagine this, then it's the curve that, considering the circle here, it has always constant angle alpha with the circles. and this lambda is the tangent of alpha. Okay, so this is the solution, and it exists only if sigma is greater than 2. And another result of Bressan, always in the same paper, is that if sigma is lower or equal than 1, then no admissible blocking strategy exists. Which is reasonable because 1 is the speed of the fire. So if we have the same speed of the fire, there's no to block it. But it's not an easy proof. So we come to the conjecture. So conjecture 2007. Let's okay, this is the result. So the conjecture, if sigma is in between 1 and 2, then no admissible blocking strategy exists. So the conjecture of Bressan, that is open from the 2007, is that we cannot confine the fire if the value of the construction speed is between 1 and 2. Okay. So before proving some theorems, I want just to present some other way to model the problem. Okay. Let me see if I told everything is wrong. Okay. So one way to model the problem is the following. One, introduce the following function. T gamma of t is the infimum, gamma of x is the infimum of time t greater than 0, such that x is in gamma of t. Which is then what is happening.
Questa non la vede più. Non la vede più questa. Ho sempre parlato Zoom.
Vabbè, forse anche c'è l'audio,
No.
la slide.
Ok.
So is it everything? Okay, so another way to model this problem is by introducing the minimum time function. What is this function here? So we take x in a 2, and we have the fire somewhere else, and we call t gamma of x is the minimum distance from the fire to x. It is the first time at which the point x is reached. But what we have, so this minimum time function morally is the solution to the Hamiltonian equation, or Hamiltonian equation, which is this one. But the problem is that because of the barriers, we do not have much regularity on this function. What we know at the present time is that this minimum time function is SBV, where SBV means that it's BV and the counterpart doesn't exist. And the jump set is concentrated on the barrier, but this is just something which is not relevant to the fire problem. I just want to say that there exists this part of theory that is present in the Lellis Probir. Is the Hamilton-Jacobi equation with obstacles. But then, so we have just this regularity on the function. But then I want to talk about another model of the fire problem, which is nicer. Sorry, I'm a bit confused today. So what we said before is that the difficulty of my fire problem is that the barrier grows with time. So the point is that if I decide to study the problem, I have to be careful because at every time the barrier can go everywhere. So another equivalent formulation, which is the one that we use the most of the fire, which is due to Bressan and Wang, is the following. Instead of assuming my strategy grows in time, I consider gamma a one-dimensional rectifiable set So I take a fixed barriers like this. So this is gamma, for example. And then I have the fire. After having given gamma, I define R gamma of T as X T such that X0 is in the starting region, X dot is in f of X, and X tau is not in gamma for every tau in 0T. Then I say that gamma is admissible if H1 gamma intersection R gamma of T is lower or equal than sigma T, and gamma is an admissible blocking strategy if again R gamma infinity, which is the union of R gamma of T, is bounded. So this problem is of course really similar to the previous one, because one can define gamma of T of before the intersection between my gamma and R gamma of T, but it's deeply different from the previous one, because here the barrier is assigned, is given, is fixed. So we can consider the fire and the intersection that the fire does with the barrier. So is it clear until now? Okay. Okay, we start with the interesting effects. A possible way to attack the conjecture of Bressan is the following. I don't remember the slide, so why I cannot. Okay. Okay. So two things before giving the tomato. Okay. So why this problem is difficult? The first reason is because the normal shades of strategies do not work in this context. So this is one result. So if gamma is a simple closed curve, then it is not admissible. Okay, so indeed, the first idea that one has is, okay, I take the fire and my gamma, which is fixed, is a simple closed curve. And why the simple closed curve is not admissible? Because on this curve, we consider the last point reached by the fire. Let's say this is P. Okay, by admissibility, we have that H1 of gamma intersection R gamma infinity, which is H1 of gamma, should be lower or equal than 2 times the time for reaching P. Let's say T minus 1. So this is C. Okay. This is the admissibility. We want that the length of the barrier has to be lower or equal than 2 times the distance until the last point, because it's the last instant of time. Yeah, okay. But then we can see that, of course, this cannot occur because a simple closed curve has length that is always greater than 2 times this quantity here. So it cannot work. But it's easy, but it cannot work. So for simple closed curve, we cannot have results. And another possible strategy that one has in mind is, okay, I don't have a simple closed curve, but I start following the fire and I decide to construct a spiral. So another possibility is a spiral. But then a result of Bressan, as you can see, only Bressan has worked with this problem. But because it's very difficult and there are few mathematicians working on it. So Bressan of 2008 is that if we have a spiral that closes, confining the fire, then sigma has to be greater than 2.6144. So there is a big gap between the interval 1, 2 and this 2.6144. Okay, so we need to examine more complicated topologies. And what I mean with more complicated topologies is this. We need, we need to introduce the internal barriers. So to summarize, we want to prove the conjecture, but it's a hope, and we cannot exploit very simple strategies as intuitive strategies as the spiral or simple closed curve. So we need that if we have a strategy, we need to construct some internal barriers that whose aim is to slow down the fire. So if this is the internal barrier, you see the fire to reach this point has to do this long trajectory. But if we remove this internal barrier, then the trajectory goes like this. So we are gaining time, and gaining time means that we are gaining length for constructing the barrier. So the difficulty is that these barriers can be whatever, because we can put inside everything. And a possibility to attack the conjecture is then thinking, okay, since I have so many possibilities, what about the optimal strategies? So the strategy that minimize the length of the barrier and the area burned by the fire. So one define the following optimization problem. So defining the cost function, given gamma an admissible blocking strategy, if it exists, one define the functional J of gamma equal to R gamma infinity, so the area burned by the fire, R of x dx, plus the integral of gamma of beta of x, H1 dx. So alpha and beta are these positive weights, they are continuous. So among all strategies, we look for those one that minimize the area burned and the length of the barrier. So the standard assumptions are alpha and beta being constant equal to 1. And this result is from Bressan and Ellis, 2012. So if there exists gamma, an admissible blocking strategy, then there exists gamma star, the optimal strategy, and an optimal strategy. Okay. So this is this result. Great. So the idea to attack the conjecture is, okay, we take gamma and we look for necessary conditions for the optimal strategy. So we want to look at those conditions that the optimal possible strategy should satisfy. And if eventually, if the strategy does not close, so if the idea is that if we manage to get the optimal strategy, so if we get gamma star and gamma star does not confine the fire, we are fine because we prove that an admissible blocking strategy cannot exist. Okay, so this is the idea. The problem is that the result of Bressan and Ellis doesn't give any important regularity on the optimal strategy. Okay, the only regularity they achieve allows just the following result. So corollary. So if gamma star is an optimal strategy, and gamma 1 subset of gamma star is a connected component, then it is compact. So our strategies, optimal strategies have only the possibilities that the connected components, so this one, and the other one, the biggest one, are compact. But this is just the regularity that one can obtain with this theory. And so there is another conjecture which is quite hard. So gamma star is the union of finitely many C1 arcs. If one is able to solve this conjecture, then thanks to this C1 regularity, one can prove necessary conditions for the optimal strategy. They have just been proved. That state how the shape of the barrier should be. But since we do not have this regularity, we cannot work with those results. So it's a really important conjecture. And there are two other important conjectures related to the optimal strategy. So this is the first one. So the optimal strategy, gamma star, is convex. And gamma star is connected. It's they are conjectures, so they can be true also. But the connectedness means that we cannot have internal barriers that float in space, but they have to be attached to the boundary. So this should be the strategy, the optimal strategy, but they are open problems. So let's come to the results that we were able to achieve. So our results are in the spirit of necessary conditions for the optimal strategy without requiring the C1 regularity. And in particular, so these are very easy observations. We did not focus on the problem. So remember the post-functional, which was the area plus length. But since the result is valid for alpha and beta positive or equal to 0, we decided to ignore the minimization of the area. So just we consider optimizers that minimize the length. Okay. So the first observation is the following. If we have gamma star, an optimal strategy, according to this minimization problem, then what we have is that our strategy should be star-shaped with respect to the direction of fire rays. So the definition is much more complicated, but basically it means that if I have an optimal trajectory that touches the boundary twice, we can simply remove this part and we substitute with this other part. So we get a strategy with shorter length, and in this case also with less area. And so we have that the optimal strategy should be star-shaped in this sense, with respect to the direction of fire rays. But the point is that here we have a convexity. Because if we forget to minimize the area, and we consider this strategy, then of course, this is useless. We cut this portion and we substitute with this portion here. So we are shortening the length, but in this case, we are increasing the area. So this result of convexity does not hold for this minimization problem, but for the original minimization problem, but it also for minimizing just the length. Okay. So we have these observations, and then we have the following result, which is the most interesting. So we have our optimal strategy that should be convex with respect to the direction of fire rays. Then we have the fire. This gamma star is optimal. So we are interested in those portions of the barrier that can be shortened, keeping the new barrier admissible. Okay. The idea here is very easy, but it's from Stefano Bianchini, so it's very nice. Don't tell him. Okay. So the idea is the following. We consider the following graph. We have here the time, and here we have H1 gamma star intersection with the reachable set. So by admissibility, if we consider sigma t, my strategy should be like this. It should lie under this constraint sigma t. This is the admissibility condition. H1 should be lower or equal than sigma t. Okay. Now we assume that there is a time interval T1, T2, which is in which the slope of the strategy is greater than sigma. So morally, we assume that the inlet T of this function is greater than sigma, strictly greater, for T in T1, T2. Okay. Now, for example, we see what is this portion here. We have, this is, for example, T1. Then we have the reachable set at time T2, so the point reached by the fire at time T2. And we assume that the slope of the function, which is this measure here, the measure of the set inside this T1 and T2, these two level sets, has a slope which is greater than sigma. Okay, then what we do? We take the endpoints of the external barrier inside this level set, and we consider but if they are not segmented, then they can be shortened. So we consider, for example, the two segments here, and we want to prove that so we call gamma R the new strategy. So gamma R is the new strategy. So instead of the previous one, we replace the portion of the external barrier with these shorter branches. And we assume that gamma R as, if we do the same graph for gamma R, as this derivative, which is greater than sigma. So we assume that also gamma R satisfy that the slope has to be greater than sigma. Then we have that gamma R is admissible. So why this? Because if we take T1 and T2, since we are shortening the length at time T2, the function of the new strategy has to be down here. So this point. Okay, now, if by contradiction the new strategy is not admissible, then the slope should be lower equal than sigma at some point. And it cannot be, because by our assumption it has to be greater than sigma. And so it has to be admissible. So basically, we can shorten those portions where the slope is greater than sigma. Okay. And which are those portions? So can we reduce the temperature of the room because I'm dying?
Well, it's not working.
Ah,
It's
great.
much more.
Can open the window, maybe?
I don't know, I can resist. So the portions that have slope greater than sigma. These are the portions burning simultaneously. What I mean for this, that one can prove, look at the drawing is better. If one has a strategy, then one has the fire. And if you consider T1 and T2, in T1 and T2, we are burning, so the fire is touching the two portions of the barrier. Okay, And this means that the two portions are burning simultaneously. And one can prove that if we have portions of the barrier burning simultaneously, then the slope is greater than sigma. And so in this kind of situation, we can, since gamma star is optimal for the length, we can substitute this portion with a segment. Okay, so this is the idea. Okay, an interesting byproduct of this result, corollary, is the following. So we assume that gamma star is my optimal strategy, and gamma star is the union of a simple closed curve, gamma 2, and gamma 1, which is a single arc. And if gamma star is optimal, then it has to be connected. So remember that the problem was to the conjecture is to prove the connectedness of the optimal strategy. But in this case, we can prove it because the idea is simple. We have the fire, and we consider the first point on the external barrier reached by the fire. And then we consider the last point reached by the fire on the external barrier. So imagine that you have the fire and it starts moving from P. Then from P, we have always two branches of the external barrier, two or more, that arrive in Q. And so by the previous proposition, the slope should be greater than sigma in this case, because I have one flame going from here, so it's starting burning this portion and also this portion. It can arrive also before here, but then we have 4 portions, so it's much more better. Great, we can apply in some sense the first homotopy result. So we can shorten the barrier until we touch the internal one. So this is the idea, the proof. This is not the proof, it's a bit more complicated. But the idea is that from the first time we reach the external barrier and the last one, we are burning with speed greater than sigma, and we can shorten the barrier. Okay? And so we prove that the optimal strategy, if we have a single arc, the internal barrier has to be connected. And another corollary is that if we have an optimal strategy with many internal barriers not touching the boundary, then there exists always an internal barrier that touches the boundary. But I don't think that this strategy could be used for proving the connectedness of the set. Maybe we can say a bit more, but I don't have any ideas about that. Okay, so these are the main ideas, and all these kind of tools were used to find the optimal strategy in a particular case, but I do not have time to analyze it, of course. So the particular case we analyzed is, okay, my strategy starts with a segment. So I have the fire and I decide to construct a wall, which is a segment. So it's a kind of intuitive strategy. Then we have just a segment, and then my strategy closes. So this segment, as told before, is always attached to the boundary. Okay, so we could characterize the optimal strategy in this specific case using the ideas of the homotopy argument, basically. And in particular, the idea is the following. So we start finding a parametrization of the set. And so on. So we have this is the parametrization of the internal curve zeta1, which is not present in this picture. And then here we have the parametrization of the external curve. Okay, the main idea is that we cannot have many oscillations. So this kind of stuff cannot occur in the optimal strategy, but I do not have time to explain why. But the first idea is that, okay, we consider this time here, which is this is the point O. So this represents the distance from the fire. So this is FO, this quantity here. This is FA. And look, since between this time we are burning always the internal barrier, when the fire arrives on the external one, so the fire is arrived touching the external one, but it is touching also the segment. So we are touching two portions of the barrier, and then I can shorten the portion of the external barrier. So basically, here the optimal strategy should be a segment. So this is the idea. I don't know. Here I don't have time. And so this is the idea. Then, so we cannot have until here many oscillations. So the figure should be like this. And then there are two possibilities. So trust me that you cannot have 3 or more oscillations. The only possibility for the optimal strategy is this one or this one. This last point corresponds to O, seen doing the whole circle, the whole parametrization. So this is O reached the second time by the fire. Okay. So the only possibilities for the optimal strategies are the two following one, and they correspond one to a segment plus a branch of logarithmic spiral as before, and the second one corresponds to a segment plus a branch of logarithmic spiral plus 2 segments. But then there is another result, corollary, there is proposition. In this setting, the 2 segments are not optimal. So basically, we cannot have this kind of situation, but the only possibility, if we have an internal barrier, which is a segment plus a branch of logarithmic spiral. But then, if one does the computation, it doesn't close. And indeed, one can do basically computations, for example, assigning the length of the segment and putting all the conditions of admissibility. One has that the angle covered by the segment, and this is for people from home, sorry. So we have the segment, another segment, here we have the fire, and then we have the logarithmic spiral. But then the angle alpha plus beta has to be less than pi. So one can do explicit computation on this particular case, finding that this angle has to be less than pi. Then this strategy doesn't confine the fire. So basically, we cannot have admissible strategies whose internal barrier is a segment. So these are the ideas, and what one should do next. So here, a collection of open problems. Of course, one should use the tools and other ideas to extend to more complicated topologies. So the first point is that the homotopy argument, the connectedness could be able just to give the shape of the external strategy. So the external strategy has to be for sure made by segments and pieces of logarithmic spirals. And this result also always and without requiring the C1 regularity of the strategy, because just of the homotopy argument and some observations. So one has that the external shape is quite easy. We can have segments and pieces of logarithmic spiral. But the first difficulty is that when we substitute this internal barrier with another barrier, we are not able to do the same analysis. Okay, so we cannot extend for the moment our result for many complicated barriers. So it's there are many open questions on this problem. So some of them are extension just to one barrier, which is more complicated than a segment. Because the point is that on the segment, thanks to Euclidean geometry, we can do easily the computations. But if we have another whatever internal barrier, we cannot do the same computations. Then an open problem is the connectedness that we know just for one portion of for one internal arc. And then there is the regularity and other questions. So this problem is very rich and nothing else. So thanks for your attention.
Thank you, Martina, for the nice seminar. Are there any questions?
I have a question. Okay, so you mentioned that for the single spiral strategy, you can only block if and only if sigma is greater than like a certain constant.
I mean, one expects that the optimal is 2.6144, but I haven't found a proof that it is the optimal. So one could have another spiraling strategy. That 2.6144 is the strategy that follows the level set of the fire. So it's always attached to the fire and it's not constructed far away from it. So it's following the fire. So one expected that has to be the optimal one, but there is no proof that among spiraling strategies is the optimal.
And how's that constant calculated?
There is a function which involves the radius of curvature. So here we have the spiral, then this is the radius of curvature. And this function involves this radius, and it's that 2.61 is the maximum of the function. Then one can prove that one can build the strategy that closes the fire, to find the fire. But there is also a work of 40 pages that does the result of Bressan of 2 lines, basically. They're exploiting some complex analysis and the intersection with the axis, but I cannot read that. But they found the same constant, so it's correct.
Okay. You never think about the little bit more different problems. So like given a instead of moving the barrier, moving the fire, eventually it's say like I give the barrier in which point of the fire is optimal.
No, we didn't consider, but of course there should be some symmetry. So the barrier should move according to the position of the fire. But honestly, I don't know how to deal with this kind of stuff. But I will think this question.
Any other question? Maybe I have a question. When you take the theorem by the Lewis and the sum on the existence of optimal
Yes.
strategy, you have this alpha and beta, no?
Mhm.
And then you said that for alpha beta equal 1, you have to be.
Oh, but,
But they have proven for alpha beta whatever,
greater than 0 and continuous.
and this can tell you something on your problem.
No, the point is that that result doesn't give any information about the regularity of the optimization, apart from the compactness of connected points.
So even if you vary alpha and beta, you don't get any information.
No, I think that it should be interesting to give some weight to area or length and to study the optimization, but honestly, I don't have any idea of how to do this kind of stuff. As you can see, I don't have ideas.
Maybe another question, it's more a clarification. When you wrote at some point the gamma star as an open problem, gamma star is convex. But what does it mean? Gamma star is a tab, right?
So I mean that the external boundary. So even if we have internal barriers, the external one should be convex. But I'm not sure that
Inside.
yes, the boundary is.
Okay, so the inside of the
And but I'm not sure that this can be, because one can have also at the internal barriers that the strategy that's like this. So we have angles that are greater than 5. But so I don't know if the conjecture is true.
okay, thank you. Question? Seems not, thank you. See you next time. Yeah. Happy